we will again continue the discussion on semi groups and their generators. Okay, so again let me start with the setup. So X a Banach space, T a semi group in X, semi group, and A its generator. So okay. So before proceeding further, let me define a concept. Okay, so this is definition. A densely defined linear operator A is said to generate a semi group so given a semi group, we know how its generator is defined, and now it's the converse. So this is the concept. So we say that linear operator generates a semi group if there exists a semi group Tt. So once a semi group is given, we know that it has generator. So whose generator is Ej. Okay, so that's the definition. So we immediately have not existence but uniqueness. Okay. A dense again, okay, that A can generate, same thing, A can generate at most one semi group. So we have uniqueness. Okay, whether a given linear operator generates a semi group or not, that's not clear at this point. But if it generates, then there is only one semi group, and this is an immediate consequence of what already you have seen. Okay, so just let me give a quick proof of that. So suppose T1T and T2T are two semi groups with generator A. Okay, so they have the same operator A as generator. Okay, so take any t positive at t equal to 0, anyhow they are identity, so they coincide, so there is no problem. So let's want to show that for any t positive, T1T is equal to T2T. Okay, so pick any x in domain of A. Okay. So, we have already seen the differentiability of the map, then this map S going to T1 T minus S, T2 S X. So, this is for 0 less than S less than T, okay, in this range. Then both the arguments are non-negative, is differentiable. Okay, and we also seen that what is the derivative. Okay, so a simple exercise using that what we did earlier, and its derivative is 0. Just check this, derivative is equal to 0. Okay, so it's a constant. Okay, so in particular, so in this interval, this mapping is a constant. So you put S equal to 0 and S equal to T and conclude that T1 T x is equal to T2 T x. So this is true for all x in dA, but dA is dense. Okay, so that's how you, but dA is dense and T1 and T2 T are continuous. So by in x, so that implies T1 T is equal to T2 T, and this T is positive, is arbitrary. So that implies uniqueness. Okay, so the existence will be the content of the Hilly-Yoshida theorem. Okay, that we will discuss next. Okay, so before that, I want to state one theorem. So this is called saturation theorem. It has important applications to PDE, especially while studying the growth of solutions. Of course, we do not have time to discuss all that thing. Apart from that, it unifies several results in analysis, notably those of Titchmarsh and Hardy-Littlewood, that I will just say that. So again the setup is TT, okay, and it generator A. Okay, so this is the theorem. So let me just state that. Okay, so there are 3 parts. So just let me state them. So let x y belongs to x be such that lim of norm a tau x minus y as tau tends to 0 plus is 0. So again let me recall this a tau, we define this as tau inverse t tau minus identity. Okay. So if it were just limit, then this is the definition of the generator. So we immediately conclude that x is in dA and Ax is equal to y, but here also the same conclusion even with this lim inf. In particular, if you assume this norm is little o of t, not the norm, this norm itself is okay, little o of 1, okay, then x belongs to dA and Ax equal to y. Okay, so the same conclusion even with this weaker assumption. Okay, this is one thing. In particular, okay, let me in particular, if y is 0, then so Ttx is equal to x for all x t greater than or equal to 0. So, in some sense x is a fixed point of this semi-group, and this will give us theorem of Titchmarsh. So, I will explain that. So, the second part, if x in dA, so we have Ttx minus x is less than or equal to supremum of norm of Tu. So, when you apply to PDE, you see these as growth rates. Norm of Ax into T. Okay, so there is a growth. And the third one, if x is reflexive, okay, so this is an assumption on the Banach space. So, that means x is identified with its second dual, and x belongs to x satisfies the relation lim if as a tau again tau dash to 0 is finite. Okay. Then x belongs to T. Okay. So, that is, so what does that mean? That is, there exists y in x such that this Ax, which is just limit a tau x so this is also useful in determining whether a function has weak derivative or not in some LP class. Okay, so compare this third condition with the first one. So, first one, of course, we have put there y, but more importantly the limit is 0. Okay, so, in other words, this third condition we can rewrite that assumptions. So, this let me just write T of tau minus identity x is O of tau. Okay, so, it is bounded by tau. So, when you divide by tau and take lim if as tau tends to 0, it is some finite number. Okay. So, whereas the first one is little o of tau. Okay. So, this is the difference. Okay. So, I am not going to prove this, but we apply this theorem to x is equal to UCB R plus, this already discussed, or LP R plus. So, again 1 less than or equal to P less than infinity, and TT is semi group of left translations. Okay. So, what do we get? So, let me just, so this we are only applying the first part of this theorem. Okay. So, let me just state that. Okay. So, on this conditions, so the x and, okay. So, if now we are using function, these are function spaces. So, let me use some functions. So, f g belong to x satisfy lim tau tends to 0 plus lim if f, so this is function, so I put that plus tau here minus f tau divided by tau minus g, whatever that now. So, if we use UCB uniformly continuous bounded functions, then we use sup norm, otherwise it is LP norm. Okay. So, this is in x. Okay. So, this is 0, then f is actually locally absolutely continuous function. So, by Lebesgue theorem f prime exists and f prime is again in x and f prime equal to 0. Okay. So, you can also use this in proving when a function has weak derivative. Okay. So, in particular, if g is 0, then f is a constant. If x is UCB R plus and f equal to 0, because the only constant function that is in LP R plus is 0. So, if x is LP. Okay. So, let me state the original theorem of Titchmarsh, then so theorem, this is Titchmarsh. If a b is a finite interval in R, and f belongs to L1 AB, and next you extend f outside AB by 0, then this A to B fx plus t minus fx dx tends to 0 as t tends to 0 implies f is a constant. No, this sorry. Just I have to put the t there. Okay, this. Okay, let me state as in the. Okay. So little o of t. Okay, so that means you divide by t and then that limit goes to 0. Okay. So you just compare this to, so this is much more complete statement of that Titchmarsh theorem. Okay, so what happens? If we replace little o t by big O t. Okay, so that will lead to theorem of Hardy-Littlewood and uses the the third part, okay, namely this one. So if x is reflexive and then these all the ratios are just bounded, then actually you say that it's in x in dA. Okay. So since all L1 is not reflexive, okay, so it's one has to, okay, the statements differ for x equal to UCB. So this is only a subspace of L infinity, okay, and L infinity as such is complicated, okay, and then x equal to L1 which is not reflexive, okay, and then we have the other one. So these are all reflexive Banach spaces. Okay, so the third part actually applies to this LP, okay, but this Hardy-Littlewood theorem stated even for this one the statements are a bit complicated, so I will not go into that, but those of you who are interested in this kind of analysis, so very nice it's hard analysis, so one can dig the literature and find out more about it. Okay. So semi-group theory in some sense unifies and it has more application even to analysis. Okay. With that digression, okay, again we back to resolvent, back to generator. Okay. So more properties. Okay. So again that setup T T A, and we have this bound omega t for all t non-negative. So m is bigger than 1 and omega is real. So in particular when m is 1 and omega is 0, Okay, if m is 1 and omega is 0, so we get norm of t less than or equal to 1 for all t greater than or equal to 0. So, this is a contraction semigroup. And in most of the applications, we encounter only contraction semigroups. In fact, the 4 examples, just check them. In the examples, all semigroups are contraction. That is very easy to check. Okay. So, this is okay. Now, with a general semigroup satisfying that and A being its generator. So, now we have this theorem. So, this is regarding the spectrum or resolvent of the generator A. So, that is so given a semigroup. So, we already saw that A is, okay, let me again recall that, densely defined closed operator. This we have already seen. Okay. So, next discussion is on the resolvent. Okay. The half plane in the complex domain. So, this is lambda such that real part of the lambda is bigger than omega. So, omega is in the estimate for the semigroup is contained in. So, this is the resolvent set. Of A. Okay. With, okay, so we have to say what's the resolvent, okay, with the resolvent of A let me put power k also. So, this is nothing but, so just lambda I minus A inverse, okay, whole power k, kth power of that operator. So, this is a bounded linear operator in X and this has this bounds. For all lambda and k equal to 1, 2, etc. all powers. Okay. So, the same m appears here, okay, and this m does not change with k. So, it is true the same m remains for all k. Okay. So, this is let me call it star. Okay. So, this is, of course, I can put a real lambda here, but the Hill-Yoshida theorem, it is sufficient to take only real lambda. Okay. So, that is one advantage. So, I am just stating that for real lambda here, lambda bigger than omega. Okay. So, this what I was saying from the beginning, that the operator should have a large resolvent set. So, here an entire half plane is in the resolvent set. Okay. So, proof is bit complicated, but I just indicate that. So, you have to study this theory of semi groups whatever needed carefully, okay, and proofs are lengthy and hard. Okay. So, proof. Okay. So, let x belongs to x. Okay. So, consider this Laplace transform. Consider the Laplace transform. Okay. So, let me call it R lambda. It depends on lambda. So, 0 to infinity e to the minus lambda t of t x dx dt. Okay. So, x is an element in the Banach space. Okay. So, here is, so we defined only for the finite interval, but here this exists as an improper Riemann integral, exists improper Riemann integral. So, you look at the Laplace transform of scalar functions and you just imitate the same proof. Okay. So, we already know that this t going to t t x is continuous. We know this, and we also have this t t of x less than or equal to m e to the omega t, right. So, combine that. So, if you take real part of lambda bigger than omega, this integral makes perfect sense. So, one then shows so this defines an operator, okay, and using this relation. So, immediately you see that R lambda is less than or equal to m by lambda minus omega. Okay. So, just remember lambda is bigger than omega. This is immediate from the definition. Okay. Just you put the norm and use this relation and you see that you can integrate that exponential. Okay. One then shows that this operator R lambda is precisely equal to this resolvent. Okay. So, that one has to verify that is indeed the inverse of this lambda I minus A inverse, and the estimates for the higher powers are derived by repeated integration by parts. So, differentiation under the integral sign. So, estimates for R lambda k are obtained by differentiation with respect to lambda. Okay. So, go through all the steps by referring to some textbooks. So, we will list a number of textbooks which you can be used. So, I will stop here and I continue with again this discussion, and then we will come to Hill-Yoshida theorem. Thank you.